All right, what is up, everyone? Welcome to week 98, building my own operating system. My camera is a little bit different today. I could not get my normal camera setup working as usual, so I'm using my laptop camera off to the side, but hopefully that should not get in the way too much. So let me just get my setup going. Today, what are we doing today? We are doing more virtual memory. Yeah, we're definitely starting a bit of a more long-term topic. And I'm just hoping to make a little bit more progress. Wait, my naming scheme was super weird here, I feel like. What have I been? I've been doing year, date, month, why? Okay, what? Okay. There's the 14th of December. Just do a quick test in the chat. What's up, Cat Flare? You beat me to it. First, I'm still gonna hit it with the test 0, just in case. Cool. Sorry, coming in a little bit late to the stream today. Let me just, yeah, so virtual memory. So last time we were working on my crazy idea of making the page table virtual address space code unit testable. Kind of a strange idea. And we sort of got it a little bit working. And the idea is to continue with that today. So, yep. What's up, Raji AF? Ragi AF, nice to see you. Yeah. What's up, Lizard? Nice to see you. Thanks for popping in. Okay. Kind of forgot what we were talking about, but what is unit testable? So it's the virtual memory code. So the code that is managing virtual address spaces, managing page tables, stuff like that. That's sort of the idea. Let me just pop open the code. Where's my water? Also, let's get that break timer going. Right. Okay. The long-term plan. Long-term project that's currently happening right now is getting the kernel's production page tables set up. Because right now the kernel is just super early in like kind of the boot stages, and it's still using the page tables from the bootloader. And we want to get onto the kernel's own production page tables. What's up, Useless? Nice to see you. Bogdan, how would you recommend kernel dev from absolute 0? This is a good chance to test out the bot, if my chat bot's working, because I think it was kind of broken. I have this resources page, Bogdan, which I send to people. It's not that good, but short answer is I would recommend taking a class. That's what I did. Okay, I think we're ready to get started. 12 people in the chat, nice. That's pretty good. Well, so let's just take a quick check-in at where we're at. So I feel like, is my text a little bit, okay. All right, so quick refresh. Let's just build everything. Building the kernel, building the unit tests, and I can run the unit tests. And currently there is a test failing, but that is just because I'm in the middle of development. And yeah, let's take a look at the unit test. And so this is the idea. So as a general principle, I'm interested in exploring how can I make as much of my kernel unit testable as possible. Unit tests meaning I can take a module of the kernel that runs in the kernel and I can kind of extract that out and I can instantiate it inside of a unit test application that runs on my developer machine as, like, for example, a Mac OS process. And that's what I mean basically. And that's sort of what we achieved last week. And so, to make the font a little small. I forget what the default font size was, but yeah, so anyway, this is my class for managing virtual address spaces. The idea is that it's going to expose sort of high-level APIs for like mapping and unmapping memory in a given virtual address space. And what I want to do, and like the actual kernel is going to make use of this class, it's going to map stuff. But while I'm developing it, I also want to have it in this unit test. And for example, I'd like to be able to instantiate the vAddress space here and then just sort of like run, call the APIs and verify that it's kind of like mutating the data appropriately, stuff like that. So yeah, and it required a bit of infrastructure to like get this going because we needed to mock out a couple of the dependencies of the vAddress space class. So for one thing, the vAddress space needs to allocate memory, and it also needs to do physical to virtual address conversions. And we need to like have mocked implementations of those in the unit test. And so, for example, in the unit test, the memory allocator is backed by malloc, normal system malloc, and the address conversion is like mocked out to basically be a no-op. Yeah, so that's just an example of that. And so now it's like, now where we actually just left off last time is like this. I was just starting out with like sketching how would this code even look like what would map even do? And this is kind of what I started with. And this is what we'll keep going with today. And yeah, I'm getting into very new territory here, so not quite sure how it'll look, but I'm just going to try to make a little bit of progress. And so right now I was just doing a bit of testing just to try testing using the allocator interface, stuff like that. But let's see. Let me just see if there were any notes from last time also. But got a lot of this stuff done actually. The address space helper is done. One thing that we're going to need that I don't have is I feel like we're going to need some types, and maybe let me also just open up my Intel manual. We might need to reference this. Okay. By types, I mean C++ classes that represent the different page table structures, like the different page table entry structures and sort of the page tables themselves. That's sort of what I have here just for testing, but let me just see if I can get back to the right place. So what? So going to somewhere, yeah, so this is the diagram. Somewhere here, it's going to be more defined exactly what the layouts are and stuff like that, but okay. So let me just think, what would be a good first step? Like basically, I just want to try just doing this. I want to map, I want to just simply map hex 100,000 to point to physical memory 1000, like the first page of physical memory. Okay, so let's just try to do this. How would I move forward with this? So basically what's going to happen is like I just need to fill out the page tables. And so let's just kind of see how that's going to look. Okay, so like some of this was okay, but I don't know, this was also kind of just very sketchy stuff. So I'm just gonna clear out some room. I mean, there's smart and there's like kind of stupider ways of doing this, I guess. Yeah, maybe I'll just try this the stupidest way. I mean, like I'm kind of just jumping ahead mentally to like kind of like some smart way, or where I have some kind of like reusable function that I can just call for each level of the page table, because the operation is basically the same at every single level, and we're just going to basically repeat this like 4 times. It's just sort of like given some virtual address, take the appropriate index chunk of it, index into the current level of the page table. If it is not present, that entry is not present, we need to allocate another one, and then basically kind of recurse and do the exact same thing. Then we go here, we look up the appropriate index, we index into the page table, we do the exact same thing like 4 times. Yeah, what's up digitalized? This is same room, different camera angle. I could not get my cameras to work today. Usually I use my iPhone, or this other iPhone I have, but I'm using like my just like literal like laptop camera right now. So same place. I need to figure that out, what's going on, but a little different perspective. That's true. Let me see. So, all right, I'm just gonna do this in the worst way. That's sort of how I'm just gonna do this in the actual worst way. So I'm gonna comment out all of this, and we're gonna come back here. So, so here's the idea. We're trying to map some memory. So let's just do that. So we get the virtual address, the destination virtual address, and we get a physical address. What I've done so far is just sort of like the initial part of this. We extract the relevant chunk. So we extract, so first we just come over here, we extract this chunk. That's what I've done over here with my dest_vazure.pageTableIndex method that I've written. This is just a helper that allows me to easily extract these different chunks from the virtual address at given levels. And I don't even need this print anymore necessarily. I'll just keep this here. Then what we're gonna do, we're gonna take, okay, PML4 table. So, right, so and this is sort of the starting point. This is passed, like the class is initialized with a pointer to the PML4 table. So it's initialized with this pointer. I don't know, yeah, that's sort of like just a random decision I made. I'm not sure that'll be the production like API of this class, but that's just how I've done it so far. So we're gonna take that, and we're going to convert that from a physical to a virtual address using the converter. And that's going to point to this thing, right? It's going to be a void star that points at this. And then what I want to do is I want to be able to index into this thing and grab specific entries out of the PML4 table. So what I want to do is I don't want to use a void star to work with this data. I want to use a typed, like some kind of type. What I've done is I've made this kind of generic page table struct, which contains an array of 512 entries. And it's templated on the specific type because maybe the idea is maybe I can reuse that for each of these different tables. I don't know, I'm still very much just sketching all of this out. But that was the idea. And so I'm going to cast that void star into an actual type. And now I actually just have a PML4 table typed object, and I can do .at PML4 index in order to index into this kind of thing. And so now we're just going to go if entry is not present, then what? So now we need to allocate another frame. So, oh, Ismail, what is up? Nice to have you in the chat. Good to see you again. Yeah, we're back at it live. Okay, now here's the part where I'm going to copy in this thing. What's up, DevRealm? Why building your OS? Just because it's a lot of fun and I'm learning a lot. So now, I mean, the naming is super weird. It's an optional physical pointer to a PDP table. I think I'm actually going to refactor this thing. Currently, I have the memory allocator set to return an optional phys adder in case the allocation fails, but I'm kind of realizing I think that was a bad decision because it's just so clunky to have it wrapped in a std optional. I think in the future, I'm actually just going to do the typical thing where a 0 pointer is invalid. I'm just going to disable. I'm just going to not allow allocating physical memory 0, basically. Okay, so now we're going to allocate this thing, and I don't know, I'm not really going to think about failures for the moment, like error conditions. I'm just going to assert that that happened. And then what do we do, actually? What do we do? We've ostensibly allocated another frame for this thing. So now we need to go in and fill in this thing to point to here at the one we just allocated. What's the goal of maps? Just map a PTE or entire user page table? Pretty much, I'm thinking it's going to be one page. Basically one PTE. Yeah. And so just as a really simple starting point, let's just say I want to map literally any memory at all into the address space, any page. That's the idea here. And so vspace.map is going to mean map the physical frame at hex 1000 into the virtual address space at hex 100,000. Yeah. Sub Umesh. How did I learn C++? I learned it a little bit in university, but I would say mainly I learned it by working at a job where I was able to use it. That's where I've gotten a lot of, the vast majority of my experience. But I also did spend a lot of time learning on it on my own by watching C++ Con talks and stuff like that. Yeah. So now I'm trying to take this entry and then fill it out. And then that's sort of the part where I need to use this struct. And I also sort of want to pull up the manual. Because to be honest, I actually AI generated this struct because it's super annoying to write these bit fields, so it's probably good points to pull out the manual. Control bit. So let me see. Okay, now we want, I feel like, let's just scroll a little bit. I'm trying to find. So this is them talking through a lot of the fine details about how the lookups work. I actually don't really know. It's a lot of details, but okay, here we go. All right, let me check the chat. Chat is popping off today. How many people? Okay, we got NSG in the chat. What's up? Yeah, we're doing paging. Maybe it's good that you're here. Yeah, I mean, yeah, Digitalize is right. I mean, yeah, making an OS is like, it's just, I mean, there are actually some YouTube channels that ostensibly teach you how to make an OS. I think Nullbyte has one. I mean, you just search for it. But I mean, Digitalized and I both have just been kind of doing online coursework, which is just sort of, you know, kind of the classic way you learn a lot of this stuff. Okay, so here it is. Here's where we get into the actual details. Table 415. I just want to double check. Okay. So pretty much the book, like the thing we're looking at right now, this is just like the Intel like x86 64 CPU manual. Okay, so here is where they really go through. All right, 20-second break, be right back. Okay, so let's just screenshot this first off. So this is going to be useful. This is just sort of what I was talking about here. No, so PML4 entry that references a PDP table. This is not necessarily relevant now. This is when you're mapping an entire gigabyte with a single, wait, interesting, with a single PDPT entry. Okay, these are the PDP entries. Page directory entry, and then so now we're back more in like the kind of normal page table entry that maps a 4K page. Cool. Oh wait, and then here's the actual diagram we want. This summarizes like everything in a single kind of thing, right? We're mostly concerned about all these basically. And then, okay, so now that I don't know, this stuff is not really relevant. Determination of access rights. Okay, then, yeah, this is where it gets into the details about how the different protections are enforced and stuff like this. Okay, cool. So now, so this is a good thing to just save. I have no idea how many lines of code this is going to be. Truly, I have no idea. Maybe a helper to walk the page tables in software. Yes. Yeah. I mean, yeah, doing it all in the map function, that's probably going to be kind of messy. So I don't think that will be the final form of this. But I could envision some kind of helper. So let's just start out by taking a look at this structure to make sure it's correct. I AI generated it because it's super annoying, but let's just take a quick look. So PML4 entry, right? And so present, writable, maybe it's present, writable, user supervisor, page write through, cache disable, accessed, ignored, accessed, ignored one, page size, wait, oh, reserved must be 0, okay. Ignored 2, okay, wait, okay, so ignored 10 through 8 though, this is 4 bits, and so that, and 11 is what? For ordinary paging, ignored for flat paging, restart. Okay, we're gonna call that ignored also. That's why it makes sense to have 4 bits there. Physical address. So then here's the actual important one, phys adder. Physical address of a 4K aligned reference this entry, bunch of reserved, and then the no execute bit on the high one. So I'm going to say that looks pretty okay. What's up, MDMA? Good to see you. Yeah. Okay. What I think I'm gonna do, I think I might AI generate the rest of these struct definitions, because frankly, this is really, and I don't really want to do that, so I'm just gonna try it out. Okay, how do I make a new chat? Show all sessions. Okay. Please generate other struct definitions for the PDPTE page directory entry and page table entry. Is that right? Sorry. 1, 2, 3, 4. Yeah. Hey, room dev, this is VS Code with GitHub Copilot. Okay. Okay, what's it saying? Added 3 new struct definitions. PDP have page size. That difference if they point to a next level or map a large page. Let's just confirm that real quick. So over here, it's saying the PS bit is reserved must be 0. Over here, it's saying page size must be 0 unless you're mapping a 1 GB page. And for the moment, I'm not going to do something fancy like that. So I think that checks out. Also must be 0, that's also here. And then what does it say over here? Page table is totally different. Okay, cool. Page table entries have a pat bit. Indirectly determines the memory type used to access. Okay, I don't know what that means. And these all include dirty and global. So let's just, so that 6 is ignored. Is this right? PDPT have dirty and global. I see a dirty on the page table, but I don't see dirty on these. So that actually looks kind of wrong. But I think I'm happy enough with this so far. Okay, quick, just audit, just to be safe. So, present, read write, user supervisor, write through, cache disable, accessed. So this is actually wrong. This is ignored. Right, that's what it says here. Page size. All I prompted it with was this. I did not give it any information other than what this text says. I sort of just assumed it would know a lot about x86 64. So ignored page size 0. Okay, what does this say? Global. Not gonna lie, don't see that. So that's I think it's sort of a similar thing as here actually. I'm just gonna call it 4 bits of, wait, what did I do? Right, so let's call this 4 bits of ignored, for ordinary paging ignored. And this reserved, ignored, execute, disable. Okay. Page directory entry, present, read write, user supervisor, write through, cache disable, accessed, also ignored, page size. Yeah, that's kind of, okay, that's, it's saying global. If page size equals 1, but I'm not seeing that, so I'm going to do the same thing. I'm going to make this 4 bits. Phys adder. I'm going to just I'm calling the first struct 3 times. Okay, some numbers 52 to 62 ignored to 63. Okay, lastly, coming in hot, page table entry. Okay, present, rewrite, user supervisor, write through, cache disable, accessed dirty. Pat. Wait, okay, wait. Global. Yeah, no, I think it saw the global in the page table entry and it like got kind of confused and generated that also in these other ones. So global bit 8 9 through 11, call that ignored, then the physical address, then the I don't know, the hard part is this M thing. I sort of like don't know what the M means exactly. But then it's saying 51. So what I'm a little bit sussed out actually, because $51 here is in the physical address. But here it's saying it should be 0. So I'm a little bit unsure about that. Okay, 52 to 62. There is apparently this protection key thing. And XD. Okay. Okay. Word. Yo, what's up, Randy? Nice to see you, man. Thanks for joining the operating system stream. Yeah, we're just deep in some CPU manuals right now. So this is sussing me out a little bit. 51 reserved must be 0. I just had an idea. Let me just 1 second. I want to maybe have another AI double check. Like I'm gonna see if ChatGPT can code review what we have. So what I'm gonna do is I'm just gonna copy in these struct definitions in here. And I'm gonna say Claude generated these struct defs for x86 64 page tables. Please code review them for me. And actually, I mean, here, since I could actually upload images into ChatGPT, because I don't think I can upload images into the Copilot thing, but actually I can just upload all this stuff. I think I'm just gonna do this. That might be kind of fun. Just gonna upload this, upload this. Upload this, page, directory entry, page, table entry. And we'll just see what happens. All right, so here's the code. Yeah, this is what that rip. You can put image in Copilot. Oh, thanks, Mario. Also, what's up, Mario? Good to see you, man. Interesting. So maybe I could have done that originally, but are there simpler architectures than Intel 64 for educational purposes? So, dude, fuck, it's printing German. Please speak English. Yeah, I mean, so Ismail, so 32-bit x86 is simpler. So yes. Yeah. x86 64, yeah. I would say, I mean, the complexity just comes from there's just more levels to the page tables. Yeah. Guys, okay. Okay, it's saying using bitfields for this is unsafe. If there's a kernel, you should fix these. Okay, so it's saying straight up don't use bit fields. Interesting. Okay, it found one error with the PML4 table. Okay. I didn't patch up the comment. Misleading. Okay. Large page, if page size is one, wait. Dirty or, large page fields are missing. If page size, then Pat moved to bit 12. Is that true? In a private project, I have just a single bit field struct, since most of these levels are similar. All right, well, it's already been 20 minutes. All right, be right back. Okay. Physical address field is misleading. It's not a full physical address. It's some portion of the physical address. Don't use these structs. Store entries like this and then use masks. Rewrite all 4 entries. Okay. I kind of want to ignore the advice I hear it on that maybe it's undefined behavior or whatever, but I sort of don't. I just don't want to use masks. Like, so what am I gonna say? Okay. I want to keep using bit fields, please, but can you generate a version with the misleading errors, comments, corrected, and say what you changed? Yeah, this is probably where I'm sort of like, my workflow is kind of bad, because now, like, ideally I would be doing this in the editor so we can show diffs and stuff. Okay, what I'm gonna do. I'm just going to commit the initial init clod structs, and now it's claiming that it needs some changes. If you insist on, did it say that? Yeah. Yeah, I'm gonna yeah, portability / layout risks. Yeah, okay. Okay. Renamed page size to reserved 0, right? So it's just important to try to get this right. So it's saying because here must be 0. Okay, cool. 6, rename from ignored. But is this even true? Oh, wait a sec. So maybe I only screenshotted the portion when this thing references a page directory. But it even has some extra knowledge, and it knows about the it knows about this stuff where the PDP-TE entry maps a 1 GB page, and that's what it's talking about actually, because I see it's saying bit 6 is either dirty or ignored. From my screenshot, it sort of seems like it was only ignored, but I wasn't looking at the full picture, because here it's saying, yeah. Okay. What's up, Ahmed? Yeah, this is a side project. Yep, just for fun. Yeah, thanks, Hex Twin. Okay, I'm just gonna clarify. Okay, for the moment, I'm only interested in entries that point to other page tables. I'm not implementing support for entries that map an entire, what was it, like gigabyte or something, or yeah, ChatGPT RFTM'd it for sure. So if we're going a little bit simpler, then apparently here are the entries. Is ignored. I want to just double check this last thing. So I'm curious about this last thing with the protection keys. Did it fix that also? Yes, wait. Did I use C++ 17? We're using C++ 23 actually, although I haven't actually used any features from it, from 23. I don't even know C++ 23 really, what's in there, but the compiler flag is on. So now is probably a good point where I can ask it about that question I had about the 51-bit. Let's just quickly take a look though. So, 52 to 58, ignored. 59 to 62, no. So that looks right. So now my last question is just going to be about this. Looks great, except the manual says bit 51 must be 0, but in your PT entry struct definition, bit 51 is in the visadder field. Is this right? Oh shit, I didn't give it the screenshot. Oh dang, okay, wow. I'm just gonna, here's the picture. Okay. Blah, 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 blah. So the table. Okay. Oh, wow. Okay, they recommend add a clarifying comment. Okay. I'm not going to take the time to like deeply understand this. I'm just going to trust the AI on this one. So let's just go back and yeah, let's just go back and take these. So I'm just going to go ahead and copy these into my code now. gonna say I actually did like having the comment on the right there. So I actually did like having the comment on the right of the bit 0. That's it. Text. You removed those. Can you please add them back? Although make sure they are accurate. They more closely matched the text in the manual. Okay, so yeah, so now we have some types. I was totally ignoring NSG's comment where he was saying he uses a single type for a lot of this stuff, and that is actually a pretty interesting approach, and probably also workable because a lot of these, like the structure is quite similar. So yeah, that might have also been a feasible approach, but I guess just for now, we're just going to do it this way. Okay. Okay, that's a little bit yucky. All right. Okay. So does this code even compile? That's the real question, because so I've been using static asserts to make sure that the struct matches 8 bytes. And if we just try to compile things. So for example, if we like made a mistake, if I accidentally allocated 2 bits to the present, the code should not even compile anymore, because now we're going past 8 bytes. So that's just a nice little kind of check you can do if these matter a lot. But apparently you're not even supposed to use bit fields for this kind of thing anyway, so interesting. Okay, so now that we have these, I'm just going to go ahead and chat GPT fixes. Now let's just baby step my way along this. So, and maybe I will pop up a copy of JOS just as a bit of a security blanket, safety blanket, sort of. Oh no, yeah, like actual JOS 2, just for reference. But just gonna try to not look like that. So let's just sort of try to do this. So, so we're at the part of mapping where we've checked the first level, and we've just seen that, okay, the entry is not present. So let's go ahead and to do, I don't know what, if, oh yeah, I don't know. Oh, interesting, actually. So in this, so we're gonna go ahead, we're going to, allocate this guy. So now what do we need to do? We need to take this entry and point it over here, which is going to involve a couple things. So entry, and instead of entry, I'm going to rename this to PML4 entry to make that a little bit clearer. So PML4 entry.present equals 1. And then, I want to, okay. Now let's point it. And to point it, we're going to set the phys_adder field to the physical address of this frame, but I think it's not the actual physical address, it's the frame number, I believe. I think that's also what the AI was trying to tell us. It's bits blah 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 of the physical address. So what would that look like? It's gonna PML4 entry dot phys_adder equals and actually, so we want the frame number, right? And I think I can get this pretty easily because remember, alloc returns a optional physical address. Physical address has this convenient frame number method. And so I think actually all I need to do is do this. Present. I'm also realizing I totally have not factored protection permissions into any of this so far. So I'll mark that as a to-do. I don't know. Take protection permissions into account. For example, we want to be able to map a page as read-only, as read-write, but potentially even execute, stuff like this. But I'm sort of not doing that right now. I'm just kind of focusing on the core aspect of this, which means I'm going to be leaving these things at 0, which means read only. Okay. So that like all that work just for, but I think that's basically kind of user supervisor, right? I mean, that's all in the whole permissions thing too. If it's 0, all right, feel free to join me for a quick stand up and stretch. Okay. The whole, I should know this, but it's kind of been a minute since I thought about it. Right, so user means is 0 means it's supervisor mode, 1 means user mode can't access this. So for the moment, again, I'm just going to assume it's all supervisor and it's just read write. Just the defaults. These are the defaults of 0. Okay, so now we need to repeat this process like 3 times. So, so now that we actually have this thing now, and it's ostensibly kind of rigged up here, we just do the exact same thing. So let me think about how I want to do this actually. let me see. So I want to, I mean, the kind of the stupidest version of this code, it's just gonna have like 3 chunks that kind of all do the same thing. And in the, you know, for example, I'm just gonna, like, the worst version of the code is we're going to have, it's going to be like a phys adder of the PDP table, right? And, you know, table equals O here. Otherwise, this thing is going to be the, oh wait, no, I can just set it here. So equals PML4 entry dot phys adder, technically shifted by kpage bits. Something like this, where this is like 12. What's up, Clark Joseph? FAQ about how this is tested, emulator stuff. Unfortunately not a lot of documentation at this point. I mean, I use Kimu, and it's not architecture independent. It's completely dependent on x86-64. There is a bit of a welcome page, I think. There is a welcome page with a bit of information about the history of this project. I don't even know if that command works, to be honest. But yeah. But feel free to join the Discord. We can chat a little bit more there. Anyway, so here's the idea. It's like we get the entry, and then we just assign the phys adder field, and then if it wasn't present, we overwrite that. You know, this is like pretty awful, like terrible code actually. But and then what we can do once we have that is sort of just repeat the process. Then we kind of do the same thing. We can, I'm gonna just copy. So what we can do over here is now we're gonna do a kind of similar thing. We're going to get the PDPT index, PDP table, and then so here we actually already, so what we need to do here is, okay, my naming. So this is the physical pointer to the PDP table. Yeah, these names are so weird. And then this is going to be actually the PDP table. And it's going to be a generic page table of the PDP entry. And here we're going to pass in the pH, blah, 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 blah. Technically, I mean, this could come a little bit after. So, sorry. So now, basically, the whole point of this, it's like we allocated it or not, or it was just there. And either way, we're going to kind of like now go over here, and the PDP points to this thing, and we're going to repeat the process, which looks like this. We got the index. We at it pt entry PDP table, and then yeah, so it's pretty clear that there are a lot of opportunities to refactor the code and extract a helper function and like do all sorts of stuff. But I just sort of wanted to sketch it out like manually before I go ahead and try to be really smart about making the code as like tight as possible. So now we're going to do like basically the exact same thing. So we have the PDP entry, and we just like, it would just look sort of like this. So now we're going to get the physical pointer to the page dir entry, right? And if the PDP entry is not present, we like do a lot of the same things. We like allocate a new page dir, PDPT entry, and page dir, right? And then last we assign page dir to page dir, and then the whole thing like repeats like one more time. And so let's probably not do that. Maybe we can think about a better way to do this. I'm going to just make a test commit temp sketching out bad way to traverse page tables. Could compile test. Okay. What's up, Pritam? Nice to see you. Does it need a mutex lock? Yes, probably. Probably all of the page table code will need to be surrounded with a lock. I mean, I'm not really, I think that's what I've seen before. Like, I think that's how Linux does it. There's like this thing called the MM lock or something like this. But I think that's a correct intuition. Okay. So what would it look like to try to improve this? So, yeah, I don't know, void func. Just if we're gonna have a function or some kind of member, and I want to say so what the general pattern is, it's going to return the pointer to the next thing. And it's either going to have to allocate that or not, or it just returns if it's already present. And so I think the return value is going to be something like a phys adder. And it's going to be passed in the phys adder of some kind of table. Like one, it's not specified exactly which of the tables it is, but basically all of these tables behave in a pretty similar way, although the reason, like, the only kind of hitch is that we end up referencing these specific types. So that either means one of two things. It either means, one, we either need to make this a template. We need to add a template argument. Or we do it NSG style, where we actually just don't really have different types for the different tables. And we just sort of have like one type that basically works for all of them for our purposes here. And yeah, I'm just gonna try the template approach. T page table. And we need a virtual address. And we also need a paging level, I think. Paging level, paging. So let's just give this a try. So I'm just gonna copy and paste in like this. And we'll just patch it up to make it work. And so we're gonna use the paging level. And we're gonna get the table index. And then now we're going to go and we're going to convert the table to its type and get the actual table. And then, so I'm gonna rename this to table. Right. Table index. Now we get the table entry. And then we get the phys adder. And no. So now it's like if table entry dot present. Interesting. We've lost code completion because it doesn't know the type of table entry. That kind of sucks. Okay. If it's present, we're just going to return table entry dot phys adder kpage bits. Otherwise, we go and do like this whole thing. Otherwise, we allocate. I'm gonna call it OPH next table because then we don't know the exact name of it. We just know it's going to be the next table in the chain. We're setting a table entry to be present. And we're setting the phys adder on the entry to point to the thing we allocated. Whew, dang, okay. So that was my initial attempt at sort of sketching out what it would look like to write sort of a generic function that is responsible, like that can be applied to like any of these three levels basically. And given the initial pointer to any of the tables and sort of a bit of knowledge about like what the table, like what level we're at and the virtual address, we go index into it and do whatever it takes in order to be able to process the next level, which could be as simple as just extracting out the physical address within the entry and returning that, or as involved as allocating a new frame for the new page table and then returning that. Dang, okay. Well, we'll see how well that works. What's up, Bizarre Zib? Good to see you finally in a live session. Nice. Happy to have you joining us. Pratam, you're stuck in a web dev role. I want to try something else. Yeah, I mean, definitely. I mean, it's honestly a bit of a deeper conversation. Yeah, it might be better if you want to email me or even chat on Discord. I'll maybe we can take that one offline. But my email's on my website. Feel free to email me if you want. We can talk about that. Okay, so now let's try to like use this code actually. And so what that would basically look like is pH table equals, I never really named this. I'm just gonna call it walk. No, I'm gonna get, I'm gonna call, I don't know, something like get or allocate next level, or get next page table. I'm gonna call it that. Oh man, now the IntelliSense is like trying to figure out how to rename this thing. Okay, so here's my attempt. I'm gonna call it get next page table. I'm going to pass in, so it needs one template argument, and then it needs a couple of it. So it needs the PML4 table, it needs the dest vadder, and then I'm going to pass in this, right? And that's what a call site looks like. That's what a call site of the get next page table function looks like. And yeah, maybe find, get or alloc next page table, something like that. So that's going to sort of just encapsulate like all this code that we previously had doing here. All that moves into that function. And now we can just try doing it again. Just gonna quickly check how the YouTube's doing. 19 people in the chat. Wow, that's pretty cool. Shout out everyone in the chat right now. Okay. So basically, let's just do it again. Right, we have. I'm just put this up here on here, and so now we're just gonna do a very similar thing. Now we're gonna get just the next level. It's gonna be the page dir, and it's gonna be. I guess what's kind of confusing is PDP entry, and we're gonna pass in the PHP table, dest vadder, and PDP table. Something like that. We lurking. First time catching a live stream. What's up, Empathy Monster? Glad it popped into your feed. Yeah, I would say this is going pretty okay. The stream got off to a bit of a slow start with a lot of this AI generated struct nonsense, but now we're writing some code. And maybe a quick little commentary about that discussion earlier. So NSG, like the whole NSG's approach versus like my approach. So my approach, which wasn't completely thought out like so clearly, but I just sort of assumed it could be useful to have C++ struct definitions that match each of the different types in the paging hierarchy. That was just sort of my intuitive approach. NSG was saying that he did it a bit differently, He basically just used a single struct with, yeah, for every level of the page table, which is actually totally possible because if you'll notice in the code, we are not using like we're not using most of the members. We're using like 2 of the members. We're using the present bit and currently and the phys adder, which are only 2 members, and those are actually consistent across every single entry type. And so it would be actually totally viable to make another struct definition that like literally had present, like, I don't know, like 50 bits, or no, like, no, however many bits of ignored, and then the 40 bits of phys adder. And that would work pretty well for us. That would be totally workable. Even in the future, if we wanted to, be using the writable, we're going to need to be able to check the writable and user bits. All of these are in exactly the same positions also. And so NSG's approach is totally workable for that. What would make that a bit harder for NSG to do it my way is I think he's using C. I'm using C++, which allows me to use templates, which allows me to still have all these different types, but then like not have to like manually duplicate like a ton of code because I can use a template. And so I think if you're using C, I think it makes a lot of sense to go with NSG's approach and just have the single one. And even for me, it could even still make sense. The downside of that approach is you sort of need to maintain, like, if we ever actually really needed full type defs for all these structs, then we would sort of need to maintain like that one like super generic one and then all of these other ones. But I don't know, maybe that's not a big downside. But just for the moment, as I sketch this out, I'm just kind of going with this more C++ heavy, kind of like type safety based approach. Yeah. Are you implementing Unix project style or going for a novel design? I think it will be a bit Unix influenced, but I also would like to use this opportunity to learn more about alternate ways of doing things, like Windows, for example, or maybe other kinds of Unixes, or even like like Fuchsia is like Google OS that's apparently really good or something. So maybe taking an opportunity to learn a little bit about that. So what I definitely don't want to do is just implement like another clone of Linux or something. To me, that sounds kind of boring. Okay, so theoretically, we've also done this. And so now we can just kind of run it one more time. And do that after a quick 20-second break. Feel free to join me. All right. Put on the hoodie. Okay. I kind of wanted to say, please generate the next line. I don't know, like, because this is like kind of mechanical. I wonder if it can kind of get it. I think it kind of did. So it's just sort of like, okay, let's go one more level. Let's just walk it one level further down. So we're going to pass, so here we passed in the pointer to the PDP table, and that got us the pointer to the page dir. And then now we've got the pointer to the page dir. We're going to walk it one more time, and we're going to get the page table. Page dir, yep. And so now we have the pointer to the page table. And Now we're pretty close to the end, I guess. Now, like, now we're gonna do something very similar. Actually, we're gonna need this, and this. And so I almost even want to extract this into a helper function. And I'm just gonna see what the AI can do. Please extract this into another private helper method that returns a ref to a table entry. What's up, Akko Beers channel? And it's doing some thinking. I hope it doesn't really screw things up. So here's the part. So I said I want to, it's going to index, get a table index, get a table, get the entry. Seems to be what's happening here. Get the index, get the table, get the entry, and we just call this right here. And I think that's all the changes, right? So that looks good to me. I'm going to keep that. And the reason I did that is because that's what I need to get here. And so now I want to, I'm going to call get table entry to get a ref to the PTE. Let's just see if it can do that for me. Looks okay. So now, yeah, so, right, so this function, we pass in page table, pass in the viator, pass in the paging level, and we're going to get a reference to the table entry. So this is going to be a PT entry. And then now we can do stuff. Well, actually, wait a second. This is like kind of similar, actually. With one exception, though. So now it's like if page table entry dot present, we do something else. What? If now, so now here's the fun kind of opinionated part. So if we get to this part of the code, I'm just going to assert false because this is the more complicated branch. If we get to this point, that means there was actually something already living in this page, in the virtual address space. And we're here trying to, like, we were given this other page to try to map into that same place. And so now we need to make a decision. From a design perspective, how do we want it to, what do we want to happen here? Do we want to fail and just simply fail saying something else was mapped here? Or do we want to just overwrite it, free that frame or something, and then put in our new one? I'm a little bit not sure. Yeah, a little bit unsure, so that's why we have the assert there. Overwrite the existing page, or simply fail. Maybe we just simply fail. Maybe we just, that's a bit simpler to just do, maybe. What's up, top-notch idiots? Building else in C++ is hard stuff. That's true. This is not easy. I'm kind of struggling a little bit. It's a header file. Yes, I'm doing pretty much most of my coding in headers at the moment. Mostly just because I'm a bit lazy to make C++ files, and it's not really a problem to do it all in headers right now. So I could, that sort of raises a question. How do I want to do error handling in my OS? I never really had to, I mean, we're at such an early point that we didn't really think about this very much. So, in this case, I don't know. I mean, yeah, there's a lot of options. Like the C style is using integers. I sort of don't want to do that. I could return an optional maybe. I could return a Boolean for success or failure, potentially. That is probably the actual easiest thing to do. Return false. I'm going to keep the assert false here just because I want. Yeah, I don't know. Just going to keep that there. But all right. Don't you use GPT? Yes, I do. I've been using it a lot this stream, actually. We were doing a lot of AI stuff earlier for the type definitions for the page tables. Okay. If it's present, then we sort of just like fail, return false. Otherwise, here's our opportunity. We're going to point the entry at the physical adder. Variants and optionals. Yeah, I mean, I do have variant available to me here. Yeah, I don't know. Are you saying that could be an error handling technique using variants? Equals frame number, something like this, return true. Variants for errors. Yeah, maybe. You know what? Now that I think about it, I don't know if I've seen that so much. But I mean, it actually does make a lot of sense. I would say that's more like I would reach for that if I have a number of distinct error conditions that can possibly contain some data associated with them. And I want to very clearly express that. But okay, optionals on the other hand, I see that all the time. We use that all the time at work, actually, optionals for return codes. Yeah, I mean, I think actually for my OS, I want to do it more like Rust style error handling, where they use these kind of like, it's called a result in Rust, and in C++ it's called stood expected. And it's basically an optional, it's basically like a bit of like a more rich optional, where instead of just getting like a null, if there isn't data, you can actually get, how does it work? You can attach data to the result or something like this. Yeah. Do I read books about system design, software, architecture? Something I struggle with personally. Honestly, like, no, not really. I don't know if I can even really claim to be that good at it. I think what I have done is it's just kind of more practical experience based. And I think I just have to say that like working full-time jobs has really helped me in that regard. Just working with code bases that other people have worked on, working with people that have experience. That's sort of how I've done it. I don't even think I've read a single book on software architecture. So I wouldn't say like, I mean, beyond the general principles of like making things testable, stuff like that. I don't know if I could even say there's like specific like techniques I like to use or stuff like this. But I can talk in more detail if you have a more specific question about that for sure. I'll just stop yapping for a second though, just to take a quick pause and kind of reflect. So we've kind of done it. This is a very extremely basic, I think somewhat complete version of a potentially working map function. Yeah. It is missing many things. It's missing support for permissions. Well, that's the main one. It's missing support for user supervisor awareness potentially. It doesn't really handle this case particularly, but it sort of just handles the straight through case where you have an address space, there's a chunk of empty address space, and you want to put something in it. So let's try and actually do this. So what I'm gonna do is I'm just gonna run the unit test and see what happens. I'm gonna compile. Does it compile? Code does compile. And what's the expectation here? So I am kind of expecting the code to hit this check false. I'm expecting it to run the vspace.map. It's going to go and just kind of do these 3 levels of the walk, fill in some data here, and set some stuff, and then return true. So I'm just going to check true. I want to check that this returns. Is this even? Okay. What? How to check true in catch 2. Oh, okay. Just the. Oh yeah. Maybe that was kind of stupid. Okay, just check. My hypothesis is we're gonna hit the check false. Let's see if I'm wrong or if I'm right or whatever. Okay. What happened? Check false on line 71. So, okay, I think my hypothesis was correct. We like got through all this. So now what I want to do is I want to even write some better, I want to write some more specific tests here. So now I'm going to call the API. And now what I want to kind of do is sort of like actually go through these data structures and verify that bits are set correctly and stuff like this. And yeah, writing unit tests is always my least favorite part. So here is where I'm again going to lean on AI and see if it can help me out with this. Please help me write a basic unit. Help me flesh out the basic unit test here. After calling map, for example, I want to test that the PML4, that the appropriate PML4 entry has the present bit set. Please implement only that part of an additional test. If that's correct, we'll go further. Right, so what I want to do is basically, I mean, I have this malloc thing. I want to basically index into this malloc buffer and cast it to this type and then check the present bit. And I think hopefully that's what it suggested for me. So p-pml4, this is our pointer to the pml4 table. We cast it to the generic page table of pml4 entry and get the table. We use this to get the appropriate index, and then we check the pml_table.at.present. So that looks perfect, actually. So I am going to take this. I'm going to ask it to extract the v-vert adder hex 100,000 into a local. Let's just kind of go with that. And let's run the tests again. And what's the hypothesis? My hypothesis is that we're going to hit the check false. And actually, I mean, I guess I can kind of remove the check false at this point. My hypothesis is that tests are going to pass, I guess. Let's just try it. Tests pass. It looks good. What's up, Mazmunir? How much time did it take you to get relatively decent at Vim bindings? Okay, I think my journey with Vim had a couple phases with it, but when I was first learning to program, I kind of got into Vim like a lot of young programmers do. I want to say I was like using it after like a year of using it maybe, but not really very advanced, I would say. But I was sort of just like able to navigate, use some tabs, use splits, which I use quite often. Stuff like that. And I had long periods of stagnation with my Vim usage where I just sort of used it in the bad ways I was using it and sort of like it was not optimal. And then more recently, I've sort of kind of gotten back into it and gotten more into things like the dot operator, which I never really used, using more of the text objects, stuff like that. But I mean, I would say within a year or so, I mean, I was decently able to do things, but then I kind of stopped for a while. So this like worked pretty well, actually. Let's try to take it one step further. So now what I want to do is I want to check that pointer. And here's like the interesting part, because the pointer, so in the real kernel, this pointer is going to be the frame number of a physical address. In the unit tests, all of these physical addresses are actually just like normal virtual addresses in the address space, but it's still going to be the frame number of what is Okay, be right back. I thought of something kind of interesting. So actually, I think I thought of a problem with this whole approach of the unit tests and stuff. So under the unit tests, what's up, Ethan? Is that an architect? Yeah, it's an architect hoodie. Nice, that's crazy. Okay, problem is, under the unit tests, the physical frame allocator is backed by malloc, which is going to return like very just like normal virtual addresses, like 64-bit virtual addresses. But I'm going to try to, I'm going to write that into the page table entry. And I don't know if I have enough bits. I think I'm just going to ask the AI about this actually. 1 second. I'm going to try to use whisper flow to dictate the message rather than trying to type that all out. Hello, 1, 2, 3. Okay. I would like some advice about my unit testing strategy. So for my kernel, my idea was to have generic portions of the kernel live in kernel lib, which is supposed to have abstract code that can either be linked into the kernel or either linked into a user space unit test. For example, in my virtual address space class, I want to unit test it, but the virtual address space class depends on number 1, a physical memory allocator, and number 2, a physical to virtual memory conversion class. So therefore, I needed to mock both of these as interfaces in the class, which seemed to work. However, what I'm realizing is that in the unit tests, the code is going to allocate, when it goes to allocate page tables, it will allocate a page of virtual address space in the user space process, but then attempt to write that virtual address space pointer into the actual page table entry. And I'm not sure if I have enough bits to actually store that address potentially. So can you think about this and help me validate or evaluate if this approach is ultimately not very well thought out? Okay, I'm gonna wall of text spam into the AI. We're gonna have it cook on that, but I don't know if I'm being clear, but maybe just to help illustrate the problem. The code that we're working on is filling in these like chunks of the entries, right? And we have a certain number of bits for them. And I just sort of am getting a bit concerned because when I go and call malloc, like I do in my tests to get kind of like the mocked frame of memory, it's gonna return a 64-bit pointer, I think. And I'm not sure I have enough bits to actually store that in here. So, yeah, speaking to the LLM. Okay, let's see what it said. You're right to be concerned. This adder is 40 bits, and so therefore this is the maximum representable number. And then on Mac, okay, so first of all, it seemed to actually understand what I was trying to say, which, well, it's like a super intelligent, AI, so hopefully it should be able to. Virtual addresses can be up to 48 bits. Okay, wait, okay. Okay, up to 48 bits. However, malloc typically returns addresses well below this, often in the whatever number this is range. So these should fit into 40 bits. However, you're not guaranteed this will always work, and it's architecturally fragile. Damn. The deeper conceptual issue, you're using user space heap points as a physical address, which works for structural testing, but doesn't this approach test well page table structure creation, index calculation bit. What it cannot test, actual address translation. Okay. yeah, no, I'm aware that I'm aware of all these. Better approach is keep it, but scope it appropriately. Your approach is actually fine for what it is. Structural unit testing, just be clear. Right. Simulated physical memory. So this actually seems like a kind of good idea. I mean, I didn't even read it, but it just seemed like a good idea. Simulated physical memory. So let me just see what it could mean by that. Let me just read the chat though. What's up, JJ? Godlike algorithm pool, thank you. OMs and compilers. Next up, use Talon for keywordless voice coding. I think I've heard about it. It's like an accessibility tool, I think, right? For like people that can't really use keyboards. Yeah, I realize we're getting like really deep into things here. We can always follow it up later in the Discord if you want to go kind of like deeper into like what we're talking about here. But yeah. So yeah, basically, I mean, I've never been completely sure about this whole like unit testing my kernel thing, and it's always been sort of like a wild experiment that might completely fail. And so far it's been like going like kind of okay. But then I had this concern about yeah, just like, can we fit when we return when we call malloc in the unit tests, we're gonna get a normal Mac OS user space pointer, which yeah, I don't know if it could fit or not into the page table entries, but it seems like it should normally fit. But then it's saying this is not guaranteed, and so then it's suggesting this thing, which is kind of an interesting idea. So I didn't even read it, but if I can guess what it means, I think it's saying, okay, instead of calling malloc just like raw, basically, try to make my own simulated physical memory allocator. Because that's what I'm trying to do here. I'm trying to sort of like simulate, you know, this VHS space code is sort of designed to be like running in the kernel. And I'm just sort of like low-key tricking it a little bit when it runs in the unit test and being like, it's going to be like, oh, hey, I need some memory for my page tables. And I'm just going to be like, okay. And I'm just here like, okay, malloc, like, here's your memory. But that pointer could sort of be like anywhere in the macOS heap. And so I think the idea here is to have a bit more control over where that pointer comes from. And what it's apparently suggesting is make a, okay, like instead of calling malloc, make my own like very limited memory allocator where I just allocate like a big buffer basically in this thing, and then I just allocate out of that buffer. Okay, so basically it's saying implement a bump allocator. And then also implement an address converter that goes along with that, which is kind of an interesting idea. And that actually does make a lot of sense. Yeah, so that is an alternative approach to my current approach of simply calling malloc and then using the NOP address converter. It's saying to basically model physical memory with a little bit more fidelity and a little bit more realism. And not gonna lie, I think that's a good idea. Yeah, like the more I just think about it, I mean, it sort of works, but not gonna lie, it's like kind of sketchy to be putting these like macOS malloc pointers into the page table entries. It is a little bit, I think it's a little bit sketchy to do that. This is a little bit cleaner, although it is more code. So it's not that much more code though. Maybe let's just read it a little bit more clearly. So we have this struct, and it's going to contain just like a big array. I'm talking like big. This thing is what, like 16 megabytes? It has a 16 megabyte array. Okay, that's pretty chunky. But I'm on like a fancy, like 64-bit computer with like some, gigabytes of memory, so that shouldn't be a problem. And then, yeah. If you go with your gut says if you think it's sketchy, don't do it. Save the headache later on. Yeah. 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 You know what? I think I like this idea. It's also just kind of a fun opportunity to use like a custom memory allocator. And I think it's a good reason to do that. Let's see. So size next frame. So basically just keeps an index. And it, so what's it doing? It just bumps it by a page every time, and then it zeroes out the frame. Right. So that's one side of it. So we're going to introduce this new specialized physical memory allocator for use in user space that's attempting to emulate physical memory. And we're going to get some pages out of that. And then as a kind of companion to that, we need to also pair this with a custom address converter that integrates and is aware of this. And the way it's going to do that is, right, so it needs to take a reference to the allocator. And yeah, okay. So then basically what does the conversion look like? All it does is the physmem is like the base, the start of the memory, and it sort of indexes into it, which is kind of interesting, which it can do because it's an array of uint8ts. And so rather than like adding physadder mem plus padder, it just kind of indexes into it. And then what about for the opposite direction? So vert to phys. So virtual means yeah, so that's going to be so the phys is like these offsets from the base, right? So we just compute the actual like real virtual address of this memory within the test. And otherwise, virtual is just the opposite direction. We basically just do a subtraction from the base, I guess. All right, let's, yeah. My recommendation, use a layered test strategy. Number one, use unit tests. Number two, use integration tests. And I think that makes sense. That's pretty much what I was planning to do anyway. But the whole reason I thought unit tests would be cool here is because, a lot of this page table stuff, it's really just sort of like generic algorithms and data structures. Allocate some memory, point some pointers around, and that's like really it. And my hypothesis was that it should be very unit testable. So let's just do it. So how do I accept this? I apply this in the editor. Oh, dang, what? Did it put it into... Oh, shit. I think I kind of wanted it in this one instead, actually. So, in test here, yeah. All right. Pop that in there. So now we have the simulated, and I'm just sort of taking the code kind of raw as it is. Let's keep it, and let's use it. So now, please use the new simulated versions of the mock classes. Okay, so we're gonna go with that. And what's up here? Oh, we don't have a free. So that, okay. And you know, well, you can't free memory with bump allocators anyway, so we're just not going to do that. Okay, so now what does it look like? So now, and also what's going on here? Conv allo, what? I wish I could read that message. What does that say? No matching constructor. What do you mean you're non-modifiable? Why can't I initialize the right now? There is a compiler error. No use after free if you never free. Funny. Interesting. Why? C++ doesn't automatically generate a constructor for aggregate initialization when you've added a reference member. Wow, okay. Not something I knew off the top of my head. I'm gonna name this allo just because I think that's a cool word, and I've been using it a lot in the code base. Call this mlo. So now, and maybe this will be the last thing we do today. So now we have kind of changed the unit test. Nothing should have changed in terms of the correctness of the code or the unit test. And so it was passing before. It should still be passing now. The only thing that's changed is we're using a little bit less of a sketchy, like, mocking mechanism. Instead of simply calling the system memory allocator and then like shoving those pointer bits into page tables, which feels a little bit odd, we're going to be more properly simulating physical memory with a custom bump allocator. And so let's compile. And let's run the unit tests. All right, moment of truth. Does it pass? Fuck, what? Damn, all right. Kill the palm tree. Assertion failed on line 7. Jeez, what the? What? Okay, what? How do I get back? I wanna just have my my easy mock adder, you know, I wanna have this stuff back just to really be sure about that. Wait, what? You know, I mean, I could try to debug that, but I'm going to not do that for the moment. I'm just going to kind of come back to here. So comment this stuff out. So just to really make sure. Wait, sorry, now I'm super confused with the state of the code. Wait a sec. So, okay. I was just trying to get back to the original working mock one. So our mock adder converter looks really simple. Our mock frame allocator. Wait a sec. So this is old, I think, right? No, this is old. The calc was the newer one. Okay, I think I've gotten it back to the previous state. Okay, all tests pass. I'm just going to tests pass, commit that. Also commit this to whip map. Oops. So now, I mean, I don't know if I'll have time to debug this in this session. So now the idea was to not use these things anymore. We're going to use this thing. I'm going to allocate the frame for the PML4 table. And that means, no, that just means we do this. So with the older way of doing this, we called malloc, got a void star, and then like sort of like weirdly like converted that into a fizz adder. But here the allo just directly returned something. So there's that. Then our converter is there, and our allocator is there. Let me just run this one more time. And it, wait, PML4, okay, what? Okay, so now this thing is like kind of complaining. It's saying, I don't know if you can see this well. So now the PML4, oh, okay, void PML4. I'm just gonna call fizz2vert and pass in the OPH blah 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 thing. MUT. Oh, test pass. Okay, cool. So sorry if that was a lot or like super deep or very hard to follow, but my main takeaway from what I'm seeing now is I think things are kind of working. Meaning our very rough changes to try to start implementing map are like slightly working. The test is very incomplete. It only checks the first level of the page tables, but at least this function like doesn't crash or something. And then not only does that like sort of work, but our unit test sort of also works, where we're able to try doing a map and then we're able to kind of go into memory and check that things look right. So we're able to check, okay, basically, did this thing get set to present in response to this map call? And then lastly, to make the test infrastructure a little bit less quote unquote sketchy, our physical memory allocator kind of, our mock physical memory allocator, we kind of changed it a little bit thanks to the AI. And we're no longer directly calling like the Mac OS or like system malloc, but we are being a little bit more controlled with it. And we have a custom bump allocator that emulates physical memory. Whew, okay, I think that's gonna be it for today, everyone. Wow. That was a pretty good stream. I felt like I was kind of nervous actually with, I don't know, like writing the page table code, like it's a little bit involved, but I don't know, this like looks kind of cool. We were able to kind of have an understanding of the general pattern of what the code looks like. And then once I kind of sketched that out, I was able to factor it out into a helper function that was a bit more generic, and then we could reduce a bit of the code duplication. So thank you very much, Ismail. Appreciate it. Thanks for locking in with me. Yeah, I think that's going to be it for today. I'm going to post my what am I going to do? I'm gonna make some asks. I'm gonna ask you to please subscribe to my mailing list if you are interested. If in what I'm doing here, I would love to stay in touch with you, and I am trying to, do that in a number of ways. I think actually I just give a command that doesn't exist. So I would appreciate it a lot if you subscribe to my mailing list. That's a great way to keep in touch. I'll be posting updates there, stuff in the future. Otherwise, I got a Discord too, and that's been going pretty well lately. We got some good conversations going on there also. So I appreciate that, Ismail. Thanks, Empathy Monster. Thanks for tuning in. And I'm still planning to be at it in the next couple of weeks throughout the holiday season. For my 100th stream, which is coming up pretty soon, so I was actually able to get a ticket to the Chaos Computer Congress in Germany this year. And that is going to coincide with the weekend of my 100th stream, actually. So I'm trying to figure out what I should do about that. I don't know if I can do some kind of event or something there or what, but I don't know. So that's just kind of coming up. But yeah, so I'm going to just end it here. M-Wave, goals of the project. I'm just trying to learn as much as I can about operating systems and make some weird shit. That's pretty much it. So yeah. All right, that's going to be it. Have a great week, everyone, and I'll see you next week.